For this film, you'll need a notebook and pencil, and you should be ready to take readings from the screen. This is part of the apparatus which we shall use to measure the velocity of light. Let's start by looking at the equipment and how it's laid out. Here's the source of the light. This is a gas laser which emits a very intense beam of what's called coherent light. We're using a laser to make observations easier, but this experiment is possible with a more conventional light source. The laser's mounted on a sturdy optical bench. The beam of light comes out from the left and falls on a slit. There it is. And the apparatus is set up so that the light which passes through the slit falls on a mirror nearly 5 meters away. This is the key to the experiment. It's a small double-sided mirror which can rotate, driven by an electric motor underneath. The speed of rotation can be controlled using a variable transformer. When the mirror's at a certain angle, it reflects the light from the slit, that's the light from the laser that's passing through the slit. It reflects that light through a lens onto a fixed mirror over 14 meters away. This fixed mirror reflects the light back again onto the rotating mirror, which in turn reflects it back to the slit. But there's a half-silvered mirror in the way, and some of the light coming back from the mirror is now reflected at right angles onto this transparent scale mounted in front of a small television camera. The scale's marked in millimeters. The camera's connected to a television monitor. Switch on the camera, and there's the scale with its millimeter divisions displayed on the screen. Later on, you'll be taking readings off this screen. Now, before we switch on the laser, we must start the mirror rotating quite slowly like this. Each time it rotates, its two faces will reflect 2 pulses of light back to the half-silvered mirror. There's the slit. Now, the laser's been switched on. If the mirror was stationary, the intensity of the light it reflected back would damage the television camera viewing the scale, so we keep it rotating and it sends back only a small fraction of the light falling on it. And there's the image of the slit projected onto the scale and looked at on the screen of the television monitor. Now look what happens if the mirror is rotated very fast, hundreds of times a second instead of only 15 to 20 times a second. It only takes the light a tiny fraction of a second to be reflected off the rotating mirror, through the lens onto the fixed mirror, and back again. But even in that very short time, if the mirror's turning very fast, it will have rotated slightly on its axis. This alters the geometry of the optical system so that the image of the slit is displaced on the scale. As you can see, it's shifted a few millimeters to the left. This displacement depends on the mirror's speed of rotation and the speed of the light which we want to measure. Let's watch the whole process as the mirror is speeded up. The image of the slit starts to move to the left. As the mirror rotates faster, the image moves further left. We can't rotate the mirror any faster than this. Now we'll slow it down again, and the slit starts to move back. The mirror's rotating slowly again. And the image of the slit is back at its first position. To get the velocity of light, we must know the speed of rotation of the mirror for a given displacement of the slit. We use this audio oscillator. The pitch of the note it gives out, its frequency, can be increased by turning this dial. We listen to it through this loudspeaker. and read off the frequency on the dial. It's reading nearly 50 at the moment, but the selector knob's at ×10, so we must multiply the dial reading by 10. And this means it's giving out a note of about, 495 cycles per second. Now, this is how the audio oscillator is used to measure the mirror's speed of rotation. We bring the mirror up to the speed we want. Then we turn on the audio oscillator and increase the frequency of its note until it gives beats with the sound from the mirror. There. When the beats die out, we're on the same frequency as the sound from the mirror. So the mirror is now rotating at 45 × 10, that's 450 cycles per second. There are the beats again. No beats, beats. No beats, 450. Now we'll start the measurements. First, let's take another look at the scale. We'll number the graduations from right to left, since that's the way the image of the slit will move. Call the long one, right of centre, 0 millimeters, then it's 1, 2, 3, 4 millimeters, and the 5 millimeter graduation is the longest one, the one on the left. Now we'll start the mirror rotating slowly so that we can switch on the laser. It makes hardly any sound at this speed, and we estimated its frequency of rotation as 15 cycles per second. Write that down, 15 cycles per second. And there's the image of the slit on the screen. Try to judge to the nearest tenth of a millimeter where the middle of the strip of light falls on the scale. It's obviously between that long mark we're taking as 0 and the 1 millimeter graduation. Write down your reading opposite the 15 cycles per second for the rotating mirror. Just to help you, we make it 0.6 millimeters. 0.6 millimeters. Now we'll bring the mirror up to a higher speed. We switch on the audio oscillator and listen for it to beat against the sound from the mirror, then find the position for no beats. There it is. Write it down. Dial reading 20.1, so that's 201 cycles per second, since we've got to multiply the dial reading by 10. 201 cycles per second. And here's where the image of the slit's been displaced to on the scale. Judge where the center of the strip of light falls on the scale and write it down to the nearest tenth of a millimeter. It's 1 point something millimeters. Remember, the center of the image of the slit. Speed the mirror up again. The image of the slit moves across the scale. And we'll use the audio oscillator again, looking for the position of no beats with the sound from the mirror. There it is. Multiply it by 10 and write it down. The image of the slit has now moved to this position. Estimate it and write it down opposite that last frequency reading. It's just past the 2 millimeter mark. Just past the 2 millimeter mark, but you judge its exact position for yourselves. We speed up the mirror again. There's the image of the slit moving further to the left. The mirror is now revolving at its new rate and will find its frequency. Remember, we have to find the position of no beats with the audio oscillator. It's somewhere around this point. There. Write it down. And remember to multiply by 10. And this is the corresponding scale reading. Judge the position of the center of the strip of light on the scale and write it down. It's not quite up to the 3 millimeters mark. Not quite up to 3 millimeters. Now for the mirror at its fastest rate of rotation. It's up to speed. Write it down and don't forget again to multiply by 10. And the last scale reading, 3-point-something millimeters. Write it down, try to judge it to the nearest tenth of a millimeter, 3-point-something millimeters. Now, as well as the readings you've taken during the experiment, you need to know two other quantities. You need to know the distance from the rotating mirror, to the fixed mirror, and from the rotating mirror to the scale. These distances are given in the notes for this film, which also show you how to use your observations to calculate the velocity of the light from the laser.